I will first introduce this concept of work by breaking down this understanding of change in energy. We have looked at kinetic and actually the three types of energy: kinetic energy, spring potential energy, and gravitational potential energy, the units of which are joules. A joule is defined as a Newton meter, which, if I expand a Newton's definition, that's a kilogram meter squared per second squared. So just kind of context of what the units are. Work can be defined as the change in energy of a system. And in the case of what we're talking about, we can consider it as the final minus the initial. So how much do I have going in? How much do I have going out? We've looked at this concept of conservation of energy. That is when the energy in the system is the same as the energy out of the system. So for conservation of energy, work is equal to 0, because the change in energy is equal to 0. But not every system is conserved. So in some cases, the energy in is not the same as the energy out. You don't really see a case where you get an increase of energy in. Usually a system loses energy through things like friction. Friction can cause loss of energy by creating heat. So you can think of it as stealing energy from a system. So again, though, this concept of work is equal to the change in energy. And the change in energy, for all the purposes of what we're going to be looking at, can, without getting into the calculus of it, can really be defined as the final minus the initial. So the final energy of the system minus the initial energy of the system. Well, that's essentially this idea of work and energy. Now, let's give you an example where I would have the system technically being not conserved, or how much work would it require to put on something. Let's say we had a mass. It could be a bag of potatoes or a block or a box, whatever it is. Let's say we have some mass. Let's say that this mass is 10 kilograms. And it's laying flat on the ground. Let's pretend that that's flat. I'm really, really bad at drawing horizontal lines. Terrible at them. Let's say it's laying flat on the ground. What would we expect this mass to do? Nothing, right? If not prompted, if nothing happens to it, it's just going to sit there laying on the ground. Newton's first law breaks this down for us, right? An object in motion will remain in constant motion unless acted on by an outside force, or an object at rest will remain at rest. This is an object at rest, remaining at rest, right, in relation to the Earth. Now, what do I have to do in order to lift this block? Let's say I want to lift this mass or this box or crate. We'll call it a box. Let's say I want to lift it to a height of, pretend I'm lifting it with a crane or whatnot. I know it's a little unrealistic to say you could just lift it 2 meters, but let's say we want to lift it to a height of 2 meters. I want to figure out how much work or energy is required to do that. You think, how much energy does the box initially start with? Well, if it's at rest on the ground, it's not moving, so it doesn't have kinetic energy. So its kinetic energy would be 0. And it's not lifted. It's right on the ground. So its potential energy, or gravitational potential energy, would also be 0. It has no energy. So in order to lift it, I have to put energy into the crate to lift it. I have to put work on it, which is why we probably, maybe not why it's called working out, but I think it's an appropriate term for working out. Why working out requires energy. You burn calories, that's burning. It has a relationship to joules, but that has the same kind of context there. It requires effort or energy to lift the box. And in this case, I could get the exact amount of work into the system by figuring out, okay, well, if the initial energy of the crate is 0, right? We talked about it doesn't have kinetic or potential. I can look at, well, what's its final energy going to be? We know in order to lift the box or the crate, I'm going to have to lift it. It's going to start moving. While it's moving, it has kinetic energy. Now, I could calculate this to get into detail, but once I get it to the height of 2 meters, let's say I'm going to leave it there. I'm going to stop it moving, or put it on a shelf or whatnot. I leave it there for all intents and purposes. Once it stops moving, it no longer has kinetic energy again. Now it only has gravitational potential energy. And that's going to be the amount of energy it's going to end up with. That's going to be its final energy. So we can actually calculate this. And we'll know finally, once it's at the 2 meters, It stops moving. It doesn't have any kinetic energy. That's going to be 0. But it is going to have gravitational potential energy. As gravitational potential energy, so the final energy, is going to be exactly related to its mass, the height at which it has been lifted to, and the gravitational acceleration of Earth. And that's going to be exactly what's going on here. I could calculate this. Its mass is 10 kilograms. Its height is 2 meters. Gravitational Earth is 9.81, but if we wanted to answer it in terms of G, we could say that the energy is going to equal 20 G in joules. That's the unit for which. That's its final energy that it has. And I can say, well, how much work was done on the crate? Well, if the work is the final energy minus the initial energy, well, the final energy was the 20 G is for gravitational Earth. You could plug in the number there. You get some finite number, but I'm being lazy with my calculator here. Joules minus the 0 joules it started with, and I get, well, it has, that's how much work is done, right? If it didn't have any energy going into it.